from the Scientific Committee on Antarctic Research. Over to you.
Thanks, Sima. Yeah. Perfect. Thank you very much. Okay, so good afternoon, everyone. We thought it might be useful to give you a glimpse about how much important the past can be for the future in terms of sea level projections. And now we will focus especially on Antarctica because, as you will see, I mean, most of the uncertainties in sea level projections are currently driven by Antarctica uncertainties about its contributions. Well, so yeah, okay, so I can go now. Okay, so should I, it was off. Oh, cool. Okay, so, well, I will just turn a little bit because I don't know my slide by heart. Well, so that's a reminder about sea level projections, the one that has been presented in the last IPCC report. And especially the blue one that represents the low emission scenarios, that is not the one committed to 1.5 degrees, but the one committed rather just below 2 degrees. And the high-end scenarios, okay, that commit to more than 4 degrees global warming by the end of the century. So the sea level projection shows that in the case of these low emission scenarios, the sea level will rise like a little bit less than a half a meter, and almost, let's say, 80 centimeters by the end of the 21st century in the case of the high-end scenarios. What is the contribution of Antarctica above those scenarios? Because all those projections represent global sea level rise. So the contribution to sea level rise is done by Antarctica, Greenland, the mountain glaciers, and ocean expansion. So Antarctic contribution by the end of the 21st century to both scenarios, as you can see, is about a tenth of a centimeter, plus an uncertainty around, let's say, 30 centimeter in the case of the worst case scenario. So you would say, why should we focus on Antarctica if the contribution is so small? Okay, it's because most of the real impacts happen on the long terms, and this is because of physics. So I will try to explain to you why we have to look at beyond the end of the 21st century and not stop at the end of the 21st century. So Antarctica is an ice sheet that rests on a continent. Most of the continent is emerged, which are the brownish areas that you can see on the bathymetric map below the Antarctic ice sheets. And parts of Antarctica also rest on the bedrock that is below sea level, okay, which are shown by all the light blue areas on the topographic map on the right. And because of that, Antarctica has a large part of the Antarctic ice sheet that is called marine-based ice sheets, which means that really the ice is anchored on the bedrock that is below sea level. This is very important because this means that Antarctica in the future will be definitely sensitive to atmospheric warming. We know that nowadays Antarctica is not melting too much at the surface, except in very northernmost part of Antarctica, in the peninsula, for example. But it also makes it very vulnerable to oceanic warming because it has the foods below sea level in those areas that are called marine-based, okay? And in those areas, by the fact that the ice is less dense than the water, when the ice flows toward the ocean, it starts floating, okay? It formed this floating platform that we call ice shelf. Those ice shelves are the ones that are really sensitive to oceanic warming. What happens is that we have been working to determine the kind of instabilities that can be generated by oceanic warming, causing disintegration of these floating parts. One of the, let's say, most discussed instabilities in our community now is called the marine ice sheet instability. It is caused really by the intrusion of warm water from the ocean that penetrates below those floating parts, floating termination of Antarctic glaciers, warm them, thin them, and then cause a disintegration, because after a while, those platforms are too thin to be sustained by the ice flow, coming from the interior of the continent, so they break in icebergs. But the role of this platform is also to maintain the inland flow and stop the discharge from inland to the ocean. So if you disintegrate this platform in front of the terminating glacier, you accelerate the ice discharge into the ocean and you rise sea level very, very fast. So this is called only by oceanic warming. So nowadays we know we are warming our ocean, so we don't know exactly where is the tipping point in terms of oceanic temperature to disintegrate this platform. That's why we are heavily working on monitoring this platform from satellite point of view. But then in the future, there might be another instabilities that will add on the marine ice sheet instability, that is caused by surface melting. So when the ice melts at the surface, the meltwater flows into the crevasse of the ice shelf, okay? And when it freezes again during the winter, it just enlarges the cracks, okay? And this causes what we call the hydrofracturing process, okay? And also disintegrate the platform very, very fast. So the both instabilities combined together cause a large retreat of the Antarctic grounding line in those sectors that are marine based, where so the ice rests below sea level. Okay, so Antarctica has two potential bombs hidden that are very slow in response, but very fast triggered by as soon as the tipping point is reached in oceanic temperature. How long does it take? A few centuries. So we have a tipping point. Probably we are very close by. That just triggers the disintegration of the platform. But we have also long-term consequences because the retreat of the grounding line doesn't take a decade. It takes really a few centuries until it finds a new equilibrium for the inland flow. Okay, that's purely ice sheet dynamics. Once the ice sheet is at equilibrium, then we can make the balance, the budget on how much ice has been lost due to this marine ice sheet instabilities. And we have calculated that in this sector, it's a multi-meter sea level rise, okay, above 4 meters. And this is an example of what have been simulated by a colleague of mine, Rob de Canton, that shows you in the future the disintegration of some sector of Antarctica that is indicated on the maps there. You see the simulation starts nowadays, and it finishes in 2300s. Okay, so it's about 3 centuries to disintegrate these parts. Okay, that's the timing. Do we know that this is not science fiction? I mean, do we have any evidence of that? So we do. I mean, I'm a paleoclimate person, so I'm looking back in the past to find the evidence. And the geological records we have found along the coast of Antarctica have shown us that those instability happened in the past many times in many different warm periods. And how do we recognize that? It's because, you know, when a glacier advances, it erodes the bedrock below the ice, okay? So it accumulates a lot of rocks and sediment in front of it. And the same happened to the ice that is grounded below sea level. It just erodes the marine bedrock and just bring forward a lot of sediment and rocks that accumulate in small mountains in front of the glaciers. Then the glacier retreats and leaves the mountains of rocks that is called a moraine. And each step back leaves a moraine. So what we do is we collect the sediments, we date them back, and then we reconstruct the instability. And in many sectors of Antarctica, so the one indicated here on the map, but also more recently in this sector that is a bit more challenging to reach, we have been finding a lot of past evidence that those disintegration of those sectors happened in this timing, a few centuries. So now we know that everything that we have been trying to push forward in our ice sheet projection in the future is not science fiction. Now let's have a perspective in the past. So this is a graphics that shows you the evolution of CO2 since the birth of Antarctica 34 million years ago. So on the left for you, yes, and up to the future 2500. Okay. And you can see that the CO2 concentration in the atmosphere was varying very much from a lot much more above 400 ppm. So when Antarctica started to glaciate, concentration was around 800 ppm. Okay, and then you can see that with time, CO2 has been decreasing, okay? And the last million year, we have having CO2 concentration lower than 300 ppm in the atmosphere, that we have been rising with our emissions very recently in the climate history. So when did it happen? So we have evidence that during that period, 23 million years ago, this happened. This is when CO2 was higher than 500 ppm, okay? So part of Antarctica disintegrated at that moment. It also happened during another period, 3 million years ago, okay? CO2 concentration was around 400 ppm, okay? This also happened when CO2 concentration was below 300 ppm. That's interesting, right? Because right now we are really screaming around that, okay, we have go through the 400 ppm threshold in atmosphere, in CO2 level in atmosphere. And so we are about to disintegrate our ices, but it already happened with much lower concentration, okay? So this means that CO2 is not the direct driver of those instabilities when the climate is cold, okay? There are other mechanisms that are due to ocean heat transport toward the ice sheet that amplify the melting from below those platforms, as I was explaining before. And so we know that's for sure. I mean, if we go well above CO2 concentration 400 ppm, we will disintegrate our sheets. Okay, so I think the paleo perspective provides you that picture. Okay, this is not that we are inventing any scenarios. So what are the sectors that really collapsed? So to do that, I mean, most of the simulations that have been performed in the past 10 years got it right before we got the geological evidence. So that's luck, maybe. But so during this famous Miocene period, okay, global mean temperature was about 5 to 9 degrees warmer than today, okay? CO2 was definitely higher than 500 ppm. Global mean sea level rise was around plus 20 to 30 meters compared to today, okay? So this implies that large portion of Antarctica were disintegrated because at that moment, Antarctica was the only ice sheet existed on the Earth, okay? There was no Greenland ice sheet or other ice sheets. Well, then during this other period where CO2 was slightly higher than 400 ppm, we have a global mean temperature higher by 2 to 4 degrees compared to today, and a sea level rise that indicator shows between 20 to 10 to 20 meters above present day sea level. Okay, same thing. As you can see, all the sectors that disintegrate are the same. Okay, a large portion of West Antarctica, and the other sectors that we indicated at the beginning where we have the evidence of geological evidence of collapse. And then the more recent interglacial period, okay, where temperature was half degree to 1 degree warmer than today. Okay, so this is what we are we are looking at Paris Agreement, which is 1.5 degrees warmer than today. Okay, so this is an example that it happens with a lower concentration of CO2 because of the astronomical configuration of the Earth that was slightly different. So the radiative heat was a bit different. But nevertheless, we had a sea level rise between 5 to 10 meters higher than today. So even with those very low variable compared to what we project in the future, we rise our sea level about this amount, okay? So now let's have a recap of every data. Okay, so we have 23 million years ago, only existing ice sheet on the Earth, Antarctica. Okay, contribution to sea level rise 20 to 30 meters. Okay, compared to today, global mean temperature higher by 5 to 10 degrees, and CO2 concentration above 500 ppm. Then we have another one period, like 2 to 4 degrees warmer than today, CO2 higher than 400 ppm, and a contribution to global mean sea level rise up to 20 meters. Then another very super warm period that we had, that's about 0.5, 1 degree warmer than today, but with CO2 around the CO2 concentration we have today, and a sea level rise about 15 meters, let's say. Then we have the last great interglacial that we had closest to us, okay? 0.5 to 1 degree, 0.5 warmer than today, with a CO2 lower than 300 ppm, okay? And we have a contribution ranging from a few meters to almost 10 meters. And this is our projections for the high-end member scenarios, okay? So 8.5 by 2300, and we are about 10 to 15 meters. So now if you compare our projection, and we have a CO2 that will be definitely larger than 500 ppm, and a global mean temperature above 4 degrees. So if you compare these projections to all the paleo period that we have and what we have been trying to reconstruct in terms of Antarctic ice sheets and Greenland ice sheet contribution global mean sea level rise, you can see that the projections are completely in the range of the paleo data. So it gives you a sense that, well, those numbers are not invented, okay? They are not coming from any synthetic simulation. They are really realistic. So what about the concept of sea level commitments? Okay, so we are speaking a lot about sea level commitments ultimately, about the fact that, well, if we follow the high-end scenario pathway, our commitment will be definitely potentially of 6 meters. But if we account for such instabilities as I described at the beginning, perhaps we could reach even 15 meters, okay, which is what paleo indicators says, basically. Well, in the lower emission scenario, actually, with instabilities, we can reach 2 meters of sea level rise. With 2 meters of sea level rise, half of the Nile Delta disappear. Okay, and well, I mean, 2 meters of sea level rise, it causes a lot of damage because sea level rise is not only sea level rising vertically, it's also combining with high tide flooding, storm surge events. So making damages within the city, even not damaging the front of the city, but also causing, for example, precipitation not draining into the ocean during extreme weather forecast events. So our sea level commitment depends, of course, on how much and how fast we mitigate our emissions. The only important things here is that we cannot avoid sea level rise. Sea level will rise anyway, but how much and how fast depends on which pathway we will be following, okay? Because this will cause an acceleration or not in the sea level projections. Very important aspect behind this sea level commitment is the climate memory of ice sheets. Okay, so in the IPCC report, it is stated that even if we stop our emission by the end of the 21st century, then ice sheet will continue to melt and to retreat or to disintegrate. And this is because an ice sheet is like the ocean. It absorbs the heat on a very long time scale. So if we stop warming it today, okay, it will just continue to melt until all the heat it has been accumulated over the centuries and millennia will be completely released, okay? So the more we warm the ice sheet today, and the more they will melt anyway, even if we recover our carbon concentration in the atmosphere. Okay, that's why we say sea level rise is unavoidable, and sea level rise of this amount is unavoidable. Okay, just because of physics of the ice. So, well, that takes a few centuries to do. Okay, so ice sheet absorbs the heat, it starts retreating. So this is what we are seeing today, and perhaps we are able to remove the carbon from the atmosphere, but the ice sheet will still retreat until the heat is completely released. Okay, so we have an absorption that is going on since a few millennia, inherited from the past. We have our current heat absorption because we are adding heat excess into the system. So it really conditions today's and future sea level rise. So with the SCAR program, we are trying to push forward the studies that use the paleoclimate into the future projections, just to provide realistic bounds and allow the ice sheet modelers to have some kind of validation of the physical processes of disintegration. So far, the communities are a bit splitted, and relying on geological evidence sometimes is difficult because we have to go there, we have to retrieve the evidence, and there are uncertainties on the evidence. But what is fairly true with Paleoclimate Archive is that if you see something happen, it really happened. Thank you. Questions? Okay.
That was a really good talk. Thank you very much for that. That was excellent. You made the point that in past climate states, the ice sheet disintegrated or retreated quite rapidly, even at levels of CO2 less than they are today. And you mentioned that was due to the configuration of the ocean and the heat from the ocean. What do we know about why the ocean was different then and how it was different?
So in terms of circulation, it was not too much difference, but so you have to think that during an interglacial period, most of the atmospheric cells are shifted southward because of the inclinations that changes and the warmer climate. So you have a stronger variability of the Hadley cell and the Ferrel cell, and then it pushes back the westerlies toward Antarctica. So it moves, it increases the advection of circumpolar deep water toward the Antarctic grounding line, actually. So it's an amplification of present-day climate, let's say. In the future, if you look at the, I'm sure you know that, but if you look at the climate projection in the future, you have a real shift of those systems toward Antarctica as well. So that's the same mechanisms.
Yeah, it's polar intensification of the atmospheric system.
Yep.
Yeah.
Yep.
Thank you.
Any other questions?
No, no question. Okay, I see that my colleague is still negotiating in the back. Well, so I know that sometimes when we speak about the past, it seems very far away. But the thing is that because of the physics, I mean, that takes so long, but that's the same way for the ocean. I mean, ocean absorbs the heat on very long time scale of few centuries to millennia. So the long-term projections are necessary to understand the system. If you only look at few decades in the future, we only have a partial view of the system. So that's the main message of it. And this is why IPCC is pushing now projection beyond the 21st century.
So we know that sea level rise is not going to be ubiquitous across the globe. Do you know? Can you hear it? Oh, okay, sorry. Hold it closer. Oh, so we know that sea level rise is not going to be ubiquitous across the globe. Do you know where it's going to be affected most by the melt?
All okay, all low-lying areas will be affected. On Saturday, we have evening, we have a UNFCCC event where people from Climate Central will illustrate on the map, on the global map, where will be the areas that will be more subject to sea level rise and experience most damage. So I encourage you to come because, yeah, you definitely will see them on the map. Okay, thanks.
Okay. So hello everyone, and apologies to those of you who have already seen this talk up to twice. My name is James Kirkham, and I am a scientist at the British Antarctic Survey. And I am going to talk to you today about why the past is really key to understanding how ice sheets are going to evolve in the future. So this is me. I've had a lot of field experience, luckily. Can you? Yeah. And that's me. That has meant for me working in some of the most rapidly changing environments on Earth. So I've done some field work in the Himalayas, and I've actually been there and seen as these places are changing before my eyes. The Himalayas are really the water towers of the world, and about 2 billion people rely on these mountains and the glaciers in them for meltwater, drinking water, and also for irrigation. I've also been there and seen the effect of people. So I've been working on glaciers there when these big clouds of pollution have been brought up from India and lower down in the continent. And all this pollution, this dark cloud you can see here, rains down onto the surface of the glaciers, darkening them, making them more likely to melt and increasing this melt in the future. I've also done some work in Antarctica, so in particular with Thwaites Glacier, which many of you might have heard of because it's the most possibly alarming glacier in the world right now. So Thwaites is about the same size as the UK or Florida and has potential to unlock the West Antarctic ice sheet and commit us to multiple meters of sea level rise in the future. So Antarctica is a really interesting place to work, really extreme, and the changes that are happening there affect us all. And this is the front of Thwaites. So Thwaites is just enormously massive. So when I was there, I was on a ship, and it took us about 2 days just to travel from one side of this glacier to the other. So it's almost unimaginably vast. It's retreating extremely rapidly. So this talk is set against the backdrop of these really striking changes that are happening on today's ice sheets. So you'll recognize that there are two main ice sheets existing in the world today. The Greenland ice sheet, which you can see on the left here. This ice sheet contains enough ice to raise sea levels by about 7 meters if all of this ice was to melt. On the right, we have a sleeping giant currently, Antarctica, which holds about 58 meters of potential sea level rise if it were to fully melt. In the videos I'm going to show you now, you can see how these two ice sheets have been changing over the last 20 years. So here, areas that are orange and getting darker are areas where the ice is being lost and are not being replenished. And areas that are actually gaining mass from snowfall, more than it's being lost, are in blue. So you see here that Greenland has rapidly lost mass across almost all of the ice sheet surface. And this is mostly due to rising air temperatures, whereas in Antarctica, most of the losses are concentrated on this West Antarctic ice sheet coast where these big glaciers, Thwaites and Pine Island, are situated. And these changes are mostly being driven by rapid changes in ocean warming. It's important to consider these changes in the long-term context of how ice sheets change. So in the past, about 20,000 years ago, the world was covered in ice sheets across North America and also Europe. And that's what this image on the slide here shows. As all these ice sheets melted away, driven by small orbital changes and how the Earth is moving around the sun, these ice sheets melted, raising sea levels by about 120 meters. Today, our last remaining ice sheets in the world are situated at much higher polar latitudes, so with Greenland in the north and Antarctica in the south. The science is clear that these ice sheets are approaching critical tipping points, which, if we are pushing these any further, they could lead to irreversible changes in these major systems. We can look at the past and examine how these sorts of changes might play out. So this graph here shows how sea level has risen over the last 24,000 years, on the left to the right. And we can look at periods where these ice sheets covering North America and Europe have previously collapsed, or have undergone one of these tipping points. And if we look at this period highlighted here, we see that sea level rose by about 18 meters in just 500 years. That's almost half a meter every decade. So my own research looks at one of the critical uncertainties about how these ice sheets today might change in the future. And that's the role of water. So today, if you go to Greenland in the summer, you'll see these enormous rivers of water flowing across the ice sheet surface. And these can pool into lakes on the ice sheet itself. We're now at a stage where there are days at a time where the entirety of the surface of the Greenland ice sheet melts in the summer. In Antarctica, we see similar spectacular melting events, but these tend to be more confined to the fringes of the continent. So in this image here, we can see a giant waterfall cascading over the edge of an ice shelf, and this is about 100 meters high. Ice sheets have incredibly connected plumbing systems, which means that the warming that happens on the surface can make its way through the ice to the bed, on which the boundary between where the ice sits on the rock beneath it. And this is really important because that water can act as a lubricating layer between the ice and the rock that helps the ice to slide more quickly towards the ocean and ultimately contribute to sea level rise. So from our current understanding of ice sheets and the changes that are happening today, we know that this meltwater is incredibly important in regulating how these ice sheets flow and how they eventually will contribute to sea level rise in the future. So the key question really is, if these events are already happening right now, what will they look like in the future under our various climate warming scenarios, such as here, here, or here? We need to understand the past and how these ice sheets have behaved in prior deglacial periods in order to understand how they're going to evolve in the future. The main problem is today's ice sheets and polar regions are some of the most inhospitable environments to work in on Earth. So temperatures in the winter can regularly drop beneath minus 60 degrees Celsius, winds can reach hurricane force speeds, and the weather can change rapidly from a glorious sunshine day to a raging storm. So it's incredibly hard to work in these environments. One answer we can use, a method we can use to address these challenges is satellites. And these have led to some fantastic discoveries. So now we can see how the ice flows from space. And so the areas that are darker purples and blues are areas where the ice is flowing more rapidly. And note here we can see the West Antarctic glaciers, which are rapidly draining this sector of the ice sheet. We can also see how the lakes on the surface of Greenland can drain over time in just a few hours, transporting vast amounts of water from the surface of the ice to the bed beneath it. Now, these methods are truly fascinating and really insightful, but they're very short. So the whole length of time that is covered by these satellite observations is about 40 years. And if that is represented, that's shown by the blue line on this screen here, we can now compare that to the length of time that ice sheets typically grow and recede over. So I'll now show you how that compares to this green line. So ice sheets can change over much longer timescales as they grow and retreat. And that's about 20,000 years. So if we look at our modern satellite observations in the context of the length of time that ice sheets can exhibit different behaviors, we see that there is potentially only a very, very small amount of time that our modern observations actually cover. So are we potentially missing something? So the way to get around this problem is to look at the past. And so in my own work, I look at the giant rivers that are created as all this meltwater flows beneath ice sheets as they melt away rapidly. And so these rivers are preserved in the geological record. And we've got an example here from Algeria. So you can see that from the scale of the buildings in the foreground of this picture at the bottom of the slide here, these massive rivers are absolutely vast. And so if you were to walk from the right to the left of one of these valleys, it would take you about 1 hour to walk from one side to the other. The image in the top right of this slide shows how ice sheets have covered the northern hemisphere over the last 3 million years. For the UK, where I'm from, the largest of these ice sheets was about 450,000 years ago, at a time when ice would have reached almost London and would have stretched across from the west of Ireland round to Russia, covering an area about the same size as modern-day Antarctica. As these ice sheets melted away, they created this massive network of rivers that are now preserved underneath the seafloor of the North Sea. And we can use these rivers to understand how ice sheets respond to extreme climatic warmth. So the way we can do this is using a technique called seismic imaging. And so we fire pulses of sound from a ship, and these travel down through the ocean into the seafloor, where they reflect off all the different buried layers of the Earth. The signals then bounce back up onto the ship, where they're collected and processed. And so what you get behind is this. So this is a 3D cube of the surface. So if I was to take a spade and dig out a big cube under our feet now, we can see all the various layers. And the really great thing about this data set is that we can go back through time. And once the IT comes back, hopefully this will play. And you can see that all the very buried layers containing these ancient glacial channels as analogs for our future warming. Give them 2 seconds to find the slide again. Okay, please just click on the video. May have to move on from this, but what you can see is, what you would see is that this cube basically goes down through the Earth, showing all the different buried layers, and then bounces back up. So that reveals multiple times that these ice sheets have grown and melted away in the past. And we can use this to unlock the secrets of what happens under the ice in periods of extreme climatic warmth. And so the work we've been doing is to use this data set to understand how ice sheets respond as they warm rapidly as analogs for the future. And so we peeled back the surface of the North Sea and revealed these big rivers in highly detailed scans. Apologies, I'll have to just wait 2 minutes for the IT to resume. Okay, we can just move on. It's okay. Okay, so there we go. Here are these buried channels underneath the seafloor of the North Sea, and they're absolutely massive. And so when we looked inside them, though, we found something even more surprising, which is that we can actually see the footprints of the ice flowing inside them, and compare these to ones that are revealed on the Earth today. And so the really important thing about this is actually that the water in these big rivers appears to be affecting how the ice flows and can tell us about how the ice might evolve in the future. So in some channels, we find these very delicate ridges, and these are created by fractured ice pushing down on the muds underneath the glaciers. And what's very significant about this particular finding is that they resemble glaciers that surge, and that is increase their flow speed up to about 100 times the normal rate before stagnating and stopping. So the presence of these particular landforms within these giant rivers shows that they have an effect to accelerate the ice flow before rapidly stagnating. In other channels, we can see big pockets which were created by icebergs drifting out as the ice disintegrated in the past. And also the features that are created by the ice actually flowing across its bed. And this shows that these particular valleys help to accelerate the flow of the ice because of all this water draining beneath them. So why are these important for? Well, we can see these landforms emerging from beneath modern ice sheets and glaciers as they recede from the landscape. And that allows us to link their presence to the behavior of the ice which formed them. So when we do this, we can categorize them into two main categories. We find some features that actually seem to slow down the flow of the ice, but many more that imply that actually all this water flowing rapidly beneath the ice sheets actually helps to speed up the ice, accelerating its flow towards the ocean. So we then began to ask, how relevant are these ancient channels for the future of our modern ice sheets? And so we went back to our data to try and figure out how quickly they actually form. And when we did, we actually discovered that there are many smaller channels buried within them. And these are quite common inside the valleys. And what this means is that the water seems to be very concentrated and can rapidly erode them. So to kind of scale this up to a bigger scale, we then turned to a model reconstruction of the last ice sheet to cover the UK. So in blue here, you can see the ice sheet growing about 30,000 years ago, bridging the North Sea. And the colors are how quickly the ice is flowing, and then beginning to retreat again. And as the ice sheet retreated, we can use the calculations to work out how much water was produced and route this underneath the ice. And when we did this, we can see that the water flows from the center of the ice to the edges, transporting all of this meltwater out from beneath the ice sheet. If we zoom in now to an area of current Denmark, we see that water can go through holes in the ice sheet surface and then is rooted in these giant channels beneath it, which is shown by the darker red colors here. And the key headline figures that we got from these simulations is that it takes just hundreds to potentially thousands of years to create these giant channels that are in some cases kilometers wide and hundreds of meters deep beneath these rapidly changing ice sheets. Smaller versions of these channels could form in just decades, so visible within human timescales. Now, these features are not only relevant as a potentially missing process in our modern ice sheet models, they're also really relevant for understanding some of the biggest challenges of our time in terms of achieving net zero through technology and energy structures. And this is because these features, or many of them, buried deep beneath the seafloor, contain deposits of shallow gas. And so in the left-hand image here, you can see in reds these features and the presence of gas within them. And this has major implications if we then want to understand where to put, for example, our wind farms in the North Sea. So this cutaway here of the Earth shows kind of a normal schematic of what the seafloor of the North Sea might look like. If we then start to consider these giant valleys, especially if they contain landforms within them, when we're planting our wind farms, the presence of gas for them is quite alarming, as they could explode if there are footings going into these landforms. Another really key implication is that if we want to then look at carbon capture and storage, which is a growing area of interest and potentially will be very vital in achieving net zero, bringing down emissions and temperatures in the long run. If you want to pump gas back into a disused or depleted oil and gas field reservoir, the fact that we have these features means that when you pump in the CO2 into these reservoirs, this could then travel through the Earth and through faults in the subsurface up to these features, where it could potentially escape out again into the oceans. So this is potentially a mechanism we need to consider when trying to evaluate how efficient these carbon capture and storage processes might be in the future. So to conclude this talk quickly, the past is really key to the future here. And we can learn a lot of lessons from the past about how ice sheets might evolve in a warming climate. Water is really inherently coupled to how ice sheets flow. And as melting and warming increases in the future, the flow of water will be increasingly important to understand when trying to predict future contributions to sea level rise. These tunnel valleys, these giant rivers flowing beneath ice sheets, are effectively the plumbing system of ice sheets in a warmer world. Our models show that water can form these valleys very rapidly within just hundreds of years potentially. And they can have a potentially stabilizing or also destabilizing impact on ice sheets in the warming world. Finally, we need to consider these features when trying to install renewable infrastructure and also trying to evaluate how effective carbon capture and storage might be in these depleted oil and gas reservoirs. So I'm going to quickly finish now by leaving this slide up here, showing the tipping points that we're rapidly approaching in our cryosphere. The record of the past is very clear. It tells us that ice sheets can exhibit rapid and profound changes that are not covered by our contemporary observations. Sea level rise on the order that has happened before, 18 meters in 500 years, is extreme. and will be very difficult for societies to adapt to. Sorry. This would be very difficult for societies to adapt to. Every 1/10 of a degree of warming that we can reduce now makes the crossing of these tipping points less likely to occur, and also buys us time to adapt to the sea level rise that we're already committed to. So the choices we're making at this COP are absolutely vital in trying to halt what are potentially very catastrophic processes that could unfold at fairly soon to be reached levels of warming. So let's make the right decisions now. Thank you very much for listening. Apologies for the tech issues, and I'll be happy to answer any questions you may have. Any questions? Sorry, wait for the mic a second.
So how much sea level rise do you feel is locked in? Let's say if we did a perfect job mitigating our emissions tomorrow, how much sea level rise do you think, how much inertia is in the system? How much higher will the sea get?
It's a great question, and we actually have this quite well calculated now. So maybe Flo could perhaps speak to this a bit more, but there was a recent study in Greenland that said that we're basically locked into, was it about 1 meter of sea level rise from Greenland? I'm going to come up here also we can answer together. So from the Greenland side.
Yeah, from Greenland, yeah, we already have at least 0.5 meter committed in any case. And as we were explaining, both James and I mean, there is this thermal inertia of the system that makes the glacier melt for a few centuries ahead. So 2 to 3 meters is something we are committed a few centuries ahead. Even if we are very good in mitigating everything tomorrow. We have to adapt. We don't have the choice.
Yeah, we have to start adapting, yes. Because even if we do, as you say, even if we do a perfect job mitigating,
it will rise anyway.
Yeah.
Anyway.
Okay.
Absolutely, but I'll add to that quickly that we are at a choice now where we can choose to adapt to still significant but lower levels of sea level rise of 2 or 3 meters. But if we continue to push these tipping points, if they're crossed, we commit to much, much higher sea level rise, and the cost of doing that will be astronomical. And so it's much better now to try and mitigate our emissions, keep the possibility of crossing these tipping points low, rather than committing to these fully and having to commit to multiple levels of sea level rise much quicker in the future. Any further questions? There's one over there.
Hey, I really enjoyed your presentation. My name is Steve. I'm a student at UNC Chapel Hill studying environmental science and remote sensing. I just had a quick question about the tunnel valleys and its relation with subglacial lakes. Is it possible that as we have more water that flows down into crevasses, fill up these basins, and then is emptied out by these tunnel valleys, do these tunnel valleys become more and more efficient as more water flows down, and possibly increasing, rates of water flowing down into the ocean over time?
Thanks, Steve. That's a really great question. So the short answer is yes. So these features are absolutely enormous, and the amount of water they could potentially carry is vast. And so as they begin to grow in a warming climate, as they switch on beneath the Earth's modern ice sheets today, they will be able to expel increasingly large amounts of meltwater. The surprising thing we found in this study is that they clearly affect the ice flow in quite complicated ways that we don't fully understand yet. So we have evidence that this water export could slow ice down or also could speed it up. And so as this happens at ever increasing rates, if we're talking about potential acceleration of ice flow, this is a factor which could be quite significant in terms of ice losses and sea level rise in the future. Another question in the front here.
I don't know if you read the book Ministry for the Future, But in that book, you may know that they were trying to pump water from the base of the glaciers up to the surface and refreeze it again. Have you thought about that at all?
So yes, there are a few papers exploring these concepts, and they're very highly cited. There's a few main issues with this. So the first issue is that we don't fully understand how these systems work fully yet, and so without understanding what would happen, you can't really predict the impact of this in the future. The second is just purely logistics, and so when you go to one of these glaciers or ice sheets, and such as Thwaites, for example, and you see the vast enormity of its scale, operating there, even for a short period of time when we were drilling through the ice and trying to extract paleoarchive records from these glaciers, is extremely challenging. And so having to do this in a warming world, or operating over the winter where it's completely pitch black, it's minus 50, minus 60, would be very, very challenging, and maintaining the equipment to do this mechanically is very hard too. There's also elements about how this would work. So what tends to happen in Greenland, for example, is that as the melt season increases, so the start of the year when we have lots of water coming into the base, the export of this water is not very efficient, and this helps to elevate pressures and push the ice through the system more quickly. But as there's more water running down there, these big channels begin to form, which expels the water out, reducing this lubricating effect and actually slowing the ice down again. And so if you were to remove this water and not remove enough, it might actually create a condition where we're not expelling it efficiently enough, and actually helping to maintain this kind of dynamic and more high pressure water system, which would then expel ice more quickly again. So that's what I mean. There's lots of kind of loop processes going on we need to understand. And so while these are possible ideas to consider in the future, I think our best choice of dealing with these problems is really to reduce emissions now, stick to what we know, and adapt for the changes that we're already locked into committing to. Any further questions? If not, Mike.
Thanks for the talk. That was really good. If I understand correctly, these channels that you found were discovered pretty much by accident. Are there now efforts underway to try and find more of these channels so they can be better measured and better understood? And where's the most likely place to look for them?
So that's a nice question. So the actual channels themselves have been known about for about, 150 years. And that's because they're so widespread. So wherever we have ice that's melted away in the past, we tend to get these big channels. What's new that we couldn't see before is all the different smaller landforms inside them. And that's simply down to resolution problems. So we've imaged these features. Infrastructure companies trying to install wind turbines, et cetera, have been plagued by these things before because they are so variable, have all these features inside them, contain gas. They're very challenging. And so, yes, I think one of the next steps would be to understand exactly the full distribution of these landforms, and then try and link their formation to the flow of ice above them, and get an idea about how they could affect Greenland or Antarctica in a warming world. Any further questions? If not, thank you very much for attending our session, and the next session will be along about half an hour. Thank you.
Test. Check mic test. Test mic. Test mic. Test mic. Test.